Our next speaker is Cyril Stachniss. Cyril.
Yes.
There. Oh, good.
Okay. Thank you very much. Could I have the slides, please? Okay, perfect. So it's my pleasure to be here and talk to you about robots and especially robotics in agriculture. I'm a professor for photogrammetry and robotics. So photogrammetry is basically image interpretation for measuring purposes. And I'm in Bonn since approximately 5 years now and working in this area of robotics, especially robots in agriculture, since a few years. And I'm happy to report here on recent activities that we have in Bonn and also give an outlook what we are doing over the next years. Then I think that this work can be really motivated well. So if you look to the growing world population and relate that to the amount of biomass that we are expected or need to produce between 2010 and 2050, so within 40 years, there's approximately the same amount that has been produced from the beginning of mankind to 2010. It's also a very catchy statement and pronounces that well, but it shows at least that there's a high demand and we need to do that in a sustainable manner. That means that also the generations after 2050 have the chance to use the resources that we have. And if we especially look to crop production, this thing I'm focusing on here today, we see that there are several demands. That means there are more humans, renewable resources compete, for example, with food production. We have also change in the demand in the sense that at least in Europe there's an increase in organically grown products or demand for that, originally grown products, and this simply changes the setup. At the same point in time, crop production has negative impacts on our ecosystems in terms of the amount of agrochemicals that we use, has an impact on biodiversity. The glyphosate discussion, you just need to follow the news and you kind of see those negative impacts. And it also has certain constraints that the amount of arable land that we have is actually limited, and climate change also poses constraints and, at least globally, will not improve our situation. So the question in the end is, how can we actually reduce the negative impacts of crop production on ecosystems and at the same point in time increase the demand, or address the demand for an increased yield? And these are two things which don't seem to be compatible. And the question is, how can we actually approach them? And that was one of the motivations where we started out, I and my colleague Heiner Kuhlmann from Bonn, around 3 years ago, setting up a proposal for a cluster of excellence, which is a larger competition in Germany for large-scale long-term projects. And with the team in Bonn and the research center in Jülich, set up a large-scale project on that. We luckily got granted. And the idea for that focuses basically, if you want to increase yield, what are the things that we can do? So there's the yield that we get from crop production, and there's kind of the potential yield, so what we can in theory get, and the actual yield that we are producing. And there are two basically knobs I can turn in order to improve those. This is one by breeding, so generating better crops, and by appropriate field management actions. I can actually increase the yield and bring the actual yield and the potential yield closer to each other. At the same point in time, if we want to reduce the inputs to the ecosystem in terms of, for example, agrochemicals, fertilizers, herbicides, for example, there are also management and breeding which give us the opportunity to reduce the required inputs, for example, by a very tailored management for plant-specific activities. So the focus of our research activity is a lot on management, but also in the support for breeding. So we're not actively doing a lot of breeding, but we're trying to generate tools with IT technology in order to provide, to support breeders. So how does that look like, and what are kind of the key milestones in crop production that we had? And if you look over the last 120 years, there have been a few key milestones basically increasing the number of people that one farmer can support from approximately 10 around 1900 to something around 150 today. And we believe that the next big step from precision agriculture into the future is actually full digitalization and fully autonomous machines. We have partial autonomy already today, but pushing this next boundary, I think, will be a big change. So that the key claims that I'm setting up, or we are setting up, is that robotics and large-scale digitalization can be a key game changer in agriculture, especially looking to crop production here, but probably also holds to other fields. I believe that autonomous systems will operate on our fields in the very near future. This can be autonomous tractors, but there are also options for building, for example, much smaller devices and have fleets with multiple of those machines. And how do they change the setup that we have? Several decisions, for example, in terms of management, will be done by machine learning, AI, I just call them intelligent systems here, exploiting large-scale data, which is important to make those systems successful. But I also believe that the integration of expert knowledge or models, how experts do their decision, into those machine learning algorithms is a challenge so that we can actually work with smaller amounts of training data and can exploit the knowledge that we have accumulated over the years as humans, and this is key for that. This has led us to this project called PhenoRob. Again, it's a very large initiative with 32 professors involved, which takes, 4 days of my work week coordinating this activity. But it's also a very rewarding activity and looks into new technologies in the area of robotics, machine learning, phenotyping for making crop production more sustainable. So what's the key approach? We basically have 3 areas. One looking into developing new technologies, which includes monitoring activities, for example, small lightweight UAVs flying over fields, monitoring fields, having autonomous robots which can drive over the fields, also doing monitoring or intervention tasks, treating individual plants specifically, and a large group of people focused on machine learning areas, dealing with large-scale data, how to integrate background knowledge. These are all aspects which are investigated here. Then a second group of investigators look into how can we improve our understanding of plant and soil, root growth, how should observations look like, what are relevant phenotypical features that I can extract without destroying the plant, what is the soil-root interaction, how can this be appropriately modeled, so that this information can then go into a modeling on a larger scale, starting from plots to fields to farms to regions, also taking economic factors into account and coming up with models that allow us to make forecasts or simulations so that we can see if we change certain input parameters, which effect will this have in certain output parameters like yield or biodiversity or spread of diseases. And bringing this together is one of the kind of big challenges that we have subscribed for and that we will hopefully push forward over the next 7 years where we received funding. So this was on a rather abstract level. I now want to go more into details and give you concrete examples about research activities that I'm doing in the lab, that other people in Bonn are doing, and giving then a short outlook how this looks like very concretely, what can we do. And the first question, which is also one which is one of the kind of 6 core projects that are in this cluster, focuses on how can we reduce the amount of agrochemicals towards more sustainable crop production. And I will start with the easiest setup here, which is actually dealing with weeds, so doing weed control on our fields. How can we do that in a better way? So first the question is, how is it done today? What's state-of-the-art weed control? So there's one thing which is conventional agriculture, where you basically drive with a tractor over the field and spray a herbicide on the whole field in order to eliminate the weed plants on that field. Alternatively, if you're in organic farming and you're not allowed to use those agrochemicals, you have to do that manually. This can be people creeping over the field or being attached to a tractor, basically driving slowly over the field, and with your hands you pick out the weed plants of the field. That's one of the reasons why organic food is more expensive, and it also is something which you can imagine doesn't scale up, so we cannot produce all the crops in that way. And one of the, let's say, hypotheses is that autonomous robots, they may not be looking like this, one of the research platforms, they will probably more look like tractors, can actually be used to improve the situation. And how could that actually work? And you can see that if you have an autonomous device or even, let's say, a smart vehicle attached to a tractor which you pull over the field, you can put a camera on that system. That camera looks downwards, and actually on that device there's here sitting a camera in this box over here, monitoring the field and taking photos. And then you need to interpret those photos and say which pixels are the crop that is growing on the field, in this case sugar beets, and which of the pixels belong to the weeds that should not be there, I want to get rid of, in order to eliminate them. So this is how it could look like. That's kind of the ideal setup. So you have a downward-facing camera, and in the camera image you have an automatic system within a few milliseconds everything which is labeled green or overlaid green in here is my sugar beet, which should not be touched, and everything which is red should actually be eliminated. And that's something that I can do with image interpretation techniques where machine learning plays an important role. So how can we build a plant classification system that from an input image you see on the left basically generates the output image on the right saying that's a sugar beet, that thing is good, everything that's red is the wheat I want to get rid of, and I shouldn't touch the background at all. So if I do that, I need to can have some way for eliminating the wheat. And there are a lot of possibilities to do that. I can still use agrochemicals, but let's say spray only the red pixels. And if you just look to the amount of red pixels versus other pixels in the image, you can imagine that you can probably reduce the amount of herbicide that you need to by 50% or 75%. Or you can do a mechanical removal by stamping those wheat plants away when they are small. So a lot of opportunities. Let's first see what we can do if we have that interpretation system of being able to classify what we see on the fields. So what we started out is actually that nowadays UAVs actually get really cheap. So what you see here is a standard out-of-the-box DJI drone, which is typically used by those of you who have kids for making nice, cool YouTube videos. So they have pretty good cameras, and they're easy to fly. You can fly them without a piloting license. So we said, okay, we take an out-of-the-box drone, fly over fields on our farm, and try to analyze the fields. Can we actually do that? And how well does it work? A couple of machine learning techniques are used. So we are especially looking here into fast deep learning methods which can be trained with small amounts of training data than those models you typically find to do general image classification on the internet, so that you put input images in there, trying to put background knowledge in there that we have about the farm for generating results with, let's say, hundreds or thousands of images and not requiring millions of training data images. And how we can do this so that it runs actually with whatever, 50 hertz, so that we can actually do that online. So if we do this, we can actually fly our field and analyze the field and say, okay, there are certain areas where everything looks good, no action is needed. Certain areas we say there's a high wheat pressure, so we may want to apply a herbicide, let's say, locally there. Or we can even say, if I look to this lower area there, actually the green pixels are smaller than in other areas of the image. So maybe some fertilization is needed there because the crop growth is slower in that area. So I can actually analyze the field on what I see. And I can also use this information to support breeders. If I have breeding applications where different varieties of a crop is planted in those different kind of small plots over there, I can use those UAVs to quite easily fly over those plots and analyze them on a daily basis and see how do they evolve, which plots show a different performance under different conditions. I can do fertilization experiments for winter wheat here, for example, and see very easily how the size of the crop changes. And I can do that at a high frequency with actually very little technical setup, and use this to support breeders and provide information as early as possible so that the breeding process can actually be optimized. Besides this, I can also use this on ground vehicles. So this is an example of one of the ground vehicles doing the first test driving over one of our fields near Bonn, in Kleinaltendorf, over a sugar beet field, with a downward-facing camera monitoring the fields. You can see this in an example over there. And then basically performing intervention actions for eliminating wheat plants that we actually see there on that field. And for doing this, I need to distinguish not only what's wheat and what's crop, I may also need to distinguish what kind of weeds I have, because some I need to spray like grass weeds, others which have a stem, I can, let's say, manually address a stem, and maybe I don't want to address the sugar beets at all, so the green things should not be touched. So I need a little bit more information, but I can also generate through these machine learning approaches now quite efficiently. And what I then can do, I can actually drive over a field. So this is an example done at ETH Zurich with one of our cooperation partners in there, in our example, and you basically see a stamping system in here, which can actually drive over a field. So this is a slow-mo video, and basically push the wheat back into the ground. This is basically a glorified Bosch nail gun that you use in construction sites, slightly modified that you can actually nail weeds into the ground. This is just one option for doing it chemical-free. There are even other options how you can do this. So this is actually an idea that we are trying out also with a startup where, oh, sorry. Can you start the video manually by clicking on it, please? So you use a laser beam for actually burning parts of that plant. So this is now a rather low power laser, a 6-watt laser, so this still takes far too long. But with more high power lasers, you can actually drive over the field and burn the relevant parts of the stem, for example. See the small white dot in the middle, and this wheat plant is very likely to die within the next days. So there are different options what you can do in order to do interventions on the field, avoiding chemicals. So in the sense what you will have selective spraying techniques which can spray individual plants. You may have laser-based techniques or thermal techniques or mechanical stamping tools that can treat plants on an individual basis and reduce the amount of agrochemicals that we need to put in the fields, on the fields. That was kind of the most simple task in these 3 key management activities: fertilization, irrigation, maybe not that much needed in Bonn, but in other places of the world, and crop protection, so dealing with diseases, especially detecting diseases very early. So this was kind of the simplest task, but also the other activities we can do from mobile platforms. Maybe we need different sensors. A normal camera may not be sufficient. We need different spectral bands or other, especially models, background information to calibrate what we see with those models. So for example, if we want to do fertilization, we need to have a model on how what the conditions of the soil, how humid is it, which plants are on there, how much fertilization has been applied in the past, in order to estimate how much, for example, nitrogen we should put on the field, to not put too much, because then it goes into the ground and drinking water, which is not desired, so that we operate under optimal conditions. Or even going a step further, if we want to address plant diseases and fertilization, we need to have more complex sensors. We need to have very good models how plant diseases spread in order to take that into account into intervention action. So there are a lot of activities which are ongoing. This is now kind of future work, what we plan to do in the next years, by combining expert knowledge about crops, simulation models, and robotics and AI technology in order to perform optimized managements. And again, this was kind of one of those examples of the things that we plan to do over the next years. And we believe that these technologies, autonomous systems, learning systems, combined with existing knowledge will be a game changer in crop production, probably in agriculture. This is one way of using new technologies to do a contribution towards higher sustainability, something that I found personally interesting and very appealing. And for that, one of the key things is, which happens right now, we need to collect more data. We need this data not only just collected, also annotated, which is a big effort. And a lot of the activities that we are doing is actually trying to find ways for simplifying those annotations or find the data samples which will make a change in the classification system in the end. So a lot of open issues in this combination of bringing these machine learning approaches into practice. Which brings me to nearly to the end of my presentation. I want to use the last 2 minutes to tell you how that all started, because it's actually related to this place over here. This started 15 years ago, or nearly 15 years ago, in Freiburg, when I started working on robotics after my PhD, and then shared the office with an Italian PhD student, Giorgio Grisetti, who later on went back to Rome, is now a professor in La Sapienza. And when he moved back, we said, we should do a cool project together, at that time working in exploration and mapping techniques with mobile platforms and mobile robots. And he said, Giorgio said, we have so many cool cultural heritage sites in Italy, we need to map all of them. So we set out and asked for exploring Roman catacombs with autonomous robots, which we got brutally rejected in the beginning, but in the second round we were successful, also thanks to the Vatican, because we needed access to the catacombs. And this was a longer process, but given that we were all technical people with very little cultural heritage background, it seemed to have been easier for us than for cultural heritage people trying to get those permissions. So we got permissions to access all the sites in Italy and had a great support here, and then built systems of these robots driving around using cameras and laser scanners to actually map sites. So personally, I spent quite a substantial amount of time, for example, here in Rome in the Catacombe di Priscilla, doing mapping tasks, and also we have been in the San Gennaro Catacombe in Naples, building high-resolution 3D models, generating camera images from those sites so that we can actually then build 3D models of the scene and then use VR glasses so that you can actually virtually walk through those places. And this was one of the examples of a part of the Priscilla Catacomb where you now can put virtual glasses on and do inspections, basically walking through those 3D models built from those catacombs. This is just kind of a small subset of this. Taking the data at that quality is quite time intensive, but it shows you what we can do with those activities and which data we can generate of those sites. This has applications for virtual tourists. Let's say if you're here in Rome, you get for free the access to a catacomb in Naples, so maybe you want to travel and see Naples as well. But there's also a lot of applications for cultural heritage sites, for maintaining those sites, for taking models, let's say, every year and comparing those models. Are there cracks somewhere? For documenting the whole process. And using this autonomous system allows you to do a lot of those tasks in a kind of nice and interesting way. And that was one of the projects which had an impact on why I got hired as a professor in Bonn, which was nice. So although this had nothing to do with the cultural heritage things I presented right now here, it was kind of a starting point which brought me to Bonn and then has led to the developments in terms of agriculture. And a lot of the techniques for mapping and interpreting images actually stem from one of those projects. So with this, I say thank you very much for your attention, and also thanks to the Vatican here for making that possible. Thank you.